This is the 4.3 video. We're going to look at sampling variability and when making inference about a population, how the sample size affects sampling variability. Sampling variability is the fact that different samples of the same size from the same population produce different estimates. Essentially, no two samples are going to give you the same results. So the larger the sample, the more accurate your results tend to be. Let's look at an example to kind of understand a little more. So I have a jar of beads at school, and last year, there's 30% of these beads in the jar are red. And last year, I had my class take a total of 80 samples from the population, and they recorded the proportion of beads that were red in those samples. And we made a dot plot. So we did it for sample sizes of 20 and sample sizes of 100. And these are the two dot plots that summarize what the distributions of the samples look like. So you can see the samples of size 100 were closer to 30 on average than the samples of 20. And so this is a good visual for the fact that larger samples tend to produce closer, more accurate predictions about a population than smaller samples do. Because you can see it's more spread out. So there's still variation in the different samples for size 100. They're just all tend to be closer on average. Let's take a look at an example here. How much do NFL players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. Do you think that 244 pounds is the true average weight of all NFL players? Explain your answer. So the answer is going to be no, because different samples of size 50 would produce different average weights. So it would be surprising if this estimate, 244.4 pounds, is equal to the average of all NFL players. So we would hope that if our sampling technique was representative, we'd hope that it would be close, but we'd be very surprised if it was exactly equal to the truth because of sampling variability. Part B, which would be more likely to give an estimate close to the true average weight of all NFL players? A random sample of 50 players or a random sample of 100 players? So again, this is just teaching the fact that larger samples are going to give more accurate estimates. And so the random sample of 100 players should be closer to the truth because the sample size is larger. Okay, let's take a look at the next objective, which is explain the meaning of statistically significant in the context of an experiment and use simulation to determine if the results of an experiment are statistically significant. So when we're doing an experiment and we notice that there is a large difference between the two groups, whatever they are, the treatments, then if there is a difference, there's really two reasons for the response to be different. Either the treatment doesn't have an effect on the groups and the difference in the response happened by chance variation in the random assignment, or the treatment actually caused the difference in the responses between the two treatments. So statistically significant means when the observed results of a study are too unusual to be explained by chance alone. In other words, if we ran the study again in the same way, we would expect the results to be similar to how they were the first time. One way I like to think about it is if I flip a coin 100 times and I ended up getting 60 heads, well, that doesn't seem too unusual to happen by chance alone. But if I flip the coin 100 times and 95 of those flips were heads, that would be surprising, and that would make me think that it's a weighted coin because surely that couldn't just happen by chance alone. That's one way to think about this idea of statistically significant. Let's take a look at a simulation problem to get a better understanding. So, is talking on a cell phone while driving more distracting than talking to a passenger? David Schreier and his colleagues at the University of Utah designed an experiment to help answer this question. They used 48 undergraduate students as subjects. The researchers randomly assigned half of the subject to drive in a simulator while talking on a cell phone, and the other half to drive in the simulator while talking to a passenger. One response, one response variable was whether the driver stopped at a rest area that was specified by researchers before the simulation started. The table shows the results below. So, of the people who talked on the cell phone, 12 stopped, 12 didn't stop, and there were 24 in the cell phone group. Of those who were passengers or talked to passengers, 21 stopped and 3 did not stop, for a total of 24. So there were 24 in both groups. 33 total people ended up stopping, and 15 ended up not stopping. So, are these results statistically significant? To find out, let's see what happened just by chance if we randomly assign the 48 people in this experiment to the two groups many times, assuming the treatment doesn't affect whether the driver stops at one area. To conduct the simulation, we are assuming that 35 stoppers and 15 are non-stoppers, regardless of whether they are talking on the phone or not. So below is a description of how the simulation was done. Basically, what they did in this simulation is they assumed that the treatments, so talking to a cell phone or talking on a cell phone or to a passenger, we're assuming that that didn't make a difference. Whether they were on the cell phone or talking to a passenger, we had 33 stoppers. So these people stopped not because of the treatments, just because they are stoppers. Because this is going to assume that the treatment didn't make a difference. So they wrote on 33 cards, stop to represent the people who stopped. And they wrote on the 15 cards, they wrote no to represent the people who did not stop. So they shuffled the cards and they dealt them into two piles of size 24 because that's the way this worked. There were 24 in each group. And then they counted how many, so the two piles represented the people who are in the cell phone and the people who are in the passenger treatment. And then they counted how many no's were in the cell phone treatment. And they recorded that number. So you can see the bottom right here is 100 trials of this simulation. So for instance, this dot right here would represent after the cards were they were shuffled and put into their piles of 24. This dot right here would be one simulation where it looks like 5 people did not stop at the rest area in the cell phone group. So the reason that we're doing this is we are wanting to know how rare was our result. Because in the study, the result was that 12 people in the cell phone group did not stop. So if you look at this trial or this simulation of 100 trials, that only happened 1 out of 100 times, which means if we really did have 33 stoppers and 15 non-stoppers, the probability or the chances of 12 of them not stopping in the cell phone group just by random chance in the random assignment process is very, very low. It only happened 1% of the time in our 100 trials. So in this case, we would say that the results are statistically significant because it was very unusual to get 12 people to stop, or to get 12 people to not stop in our simulation. So again, yes, the results are statistically significant. In 100 trials, only once did 12 or more people fail to stop when using a cell phone. Since a result of 12 or more is unlikely to happen due to chance variation in random assignment, the results are statistically significant. Looks like talking on the cell phone caused more people to miss a stop. So one should be aware of the wording here. There is chance variation in random assignment. That's what this simulation was repeating over and over again. If there were 33 stoppers and the treatments didn't make a difference, then what are the chances that these 12 of them were assigned to the cell phone group. Well, we did it over and over and over again, and that only happened 1 out of 100 times. So that means this number of people, 12 missing the stop, couldn't have been due to chance variation random assignment. It must have been because of the cell phone. The treatment was actually influencing their response. Let's take a look at the last objective, identifying when it's appropriate to make inference about a population and when it's appropriate to make inference about cause and effect. And it's really quite simple. If there was random selection done, then you can make inference about a population. If there was random assignment, then you can make inference about cause and effect. This table here summarizes it pretty well, perfectly. If there was random selection and random assignment, you can make inference about population and cause and effect. If there was random selection, but there was not random assignment, then you can make inference about the population, but not about cause and effect. Let's take a look at an example of a problem you might see about this. Many students insist that they study better when listening to music. A teacher doubts this claim and suspects that the listening to music hurts academic performance. The teacher selects a random sample of 30 students from the school to participate in the study. Each of the selected students is asked whether he or she studies while listening to music. And then their GPAs at the end of the semester were recorded. So the results showed students who listened to music while studying generally had lower GPAs than students who didn't listen to music when studying. What conclusions can we draw from this study? Explain your answer. So the students were randomly selected for this experiment or this study, but since they weren't randomly assigned, we can't make any conclusion about cause and effect. So really, all we can say is we can use this sample to draw inference about the population, which would be all the students at this school, and we can say that the students at this school who listen to music while studying have lower GPAs, but we can't say it was caused by them listening to music because they weren't randomly assigned to treatments. So this also I wanted to say was the concept, or it's called the scope of inference.